All right, so before we get started, I just wanted to show you some things to look forward to as we're working through this project. This is just a Blender mesh that I loaded into Vulkan. It's the classic monkey head. And this is just a cube with a texture on it. So those are two things we have to look forward to, being able to load textures and meshes from Blender. But before you go into this video, I really encourage you to look at the Vulkan documentation and read about pipelines. This is going to have you have a better understanding of what's going on. All right, so to display, there's something I want to display, and I'm going to do this real quick here. So I'm going to make a new empty little canvas here. And I just want to explain in short terms what rasterization is. So if you really want to look into this into more detail about rasterization, Biscuit does a really good job at this. He even shows the formula used for interpolation, and it gives you a better idea of what's happening. All right, so if I want to get into this, I'm going to explain this really simply. You'll have to go into this more yourself if you want, but there's a difference between samples and pixels, and depending on how you have things set up, this can be a little different. But just know that a sample is part of a pixel. A pixel is made up of multiple samples. You can have a pixel. I think there is a way a pixel and a sample can be the same. Like one pixel is the same as one sample. But anyways, I'm not going into that. So we have our grid here. You can just imagine this as, for simplicity, is multiple cells that are being drawn onto the screen at a time. And we're, filling it in from top to bottom. We're just going to fill in each one of these colors, right? And what our graphics pipeline is going to do is we're going to store vertices, or so let's say we have a vertice here, a vertice here, and a vertice here. Typically in 3D graphics, you typically want to make triangles, because with a triangle, it's a simple plane. And no matter how you position these three vertices, it's always going to be, I'll explain this simply, flat. And that's kind of what we want. So what's going to happen here is, as our pipeline is going through all these grid cells, it's going to be like, oh, okay, well, there's a line from here to here. Like, it's going to do some interpolation and be like, okay, well, you're crossing this line, so let's fill in this grid cell. Say you chose the color pink. So it's going to fill in this grid cell right here. Then it'll fill in the next one, the next one, the next one, whatever, until it hits here. And let's say it fills in this area too. Right? Kind of like that. And then it sees this spot over here, and it uses the interpolation. And then it fills in all the way to here. And then it says, oh, wait, we got to fill in over here too. So boom, fills in all these cells. And it fills in, depending on if it's filled or not, it'll fill in all of the area in the middle. Like that. And you can see that there's some jaggedness to this process, and there's ways of removing that and whatnot. But yeah, I'm just simplifying it for you. And to simplify this a little more, when we get into shaders, I haven't really explained what shaders are yet, but there's vertex shaders and there's fragment shaders. You can kind of think of the vertex shaders as those red points we made. And you can think of the fragment shaders as those pink colors, the pink grid cells that we filled in. It doesn't have to be pink. It could be other colors. And there's more to this than just what I'm mentioning, but this is a very simple explanation. we are going to start to create our vertex and fragment shader. So to do that, we're going to modify our make file a little bit. And what you'll want to have installed is a program called GLSLC. And what that does is it compiles our shaders into .spv. And if you're still clueless about what shaders are, you can kind of think of it like this. There's vertex and fragment shaders. What I kind of mentioned already with that examples and on the grid. So the vertex shaders are for vertices. Fragments are for, the colors. And there's a specific language for the vertex and fragment shaders that we can use to describe how we want our vertices or fragments laid out. And we can do that through the GLSL language, which is originally was made for OpenGL, but you can use it for Vulkan as well. You could also use HLSL, but I'm not going to be covering that. And SPIR-V stands for Standard Portable Intermediate Representation. It's the compiled or like the binary format that Vulkan uses for its shaders. And real quick, I just updated the make files so that we can compile our fragment and vertex shaders. All right, so I added 2 more files, our triangle.frag and our triangle.vert. So as we're going to be working through this vertex shader, I want you to keep in mind that GLSL is going to use NDC or normalized device coordinates. So the coordinates kind of work as you see in this image here, where 0, 0, 0 is the center, 1, 1, 1 is the back top right, and -1, -1, -1 is the front bottom left, and so on. We're going to be working with 2 dimensions, so you can kind of ignore the 3-dimensional aspect of this for now and just focus on the X and Y. All right, so in our vertex shader, you can see that we have our 3 XY coordinates for our triangle. Then in main here, we're going to use a vec4, and this vec4, this is the X and Y coordinates, this first argument. This is Z for the second argument and W for the third argument. So the first argument, we're going to take that positions array we created, and this is this GL vertex index variable is actually a built-in variable. And what it's going to do, it's going to run through each element in our array. And this GL position variable is also a built-in variable. And what this variable does is a mandatory output that tells the rasterizer where the point is on the screen. All right, and then before we move on to this fragment shader, I just want to describe kind of the execution order. So the vertex shader is read first. It outputs the GL position. Then the rasterization process happens. The GPU takes positions from the vertex shader and determines which pixels on the screen fall inside the resulting triangle, like we showed earlier. Then the fragment shader is read and processes the pixels identified by the rasterizer, and it outputs the final color. All right, so now in our fragment shader, we set the layout location equals 0. This tells Vulkan which attachment in your frame buffer should receive this color. So in this case, we are telling Vulkan the location of 0, which this is going to refer to the first color buffer, which is our swap chain image. Then we have the word out. This marks the variable as an output that leaves the shader and heads out towards the GPU's blending hardware. Then we have this vec4, which is an RGBA format. So In this case, we're just saying we want a red triangle that's fully opaque. All right, and then I have two functions here, this read file and load shader function. So this read file just reads all of our it'll read an entire file and then set it as a string and return that string. And our load shader will get that file as a string. It'll take it as this code variable with the size that we supplied to it. We're going to create a VK shader module. We're going to make sure, check that that's good. We're going to free the chart pointer that was created from read file and return the module. I am going to create the pipeline layout and graphics pipeline global variables. And we're going to create our create graphics pipeline function. We have our vert module or frag module. We have our VK pipeline shader stage create info. We're having the type, we're going to have two stages, which is our vertex and fragment stage. And we're just going to say this is a shader struct. And then we're going to say this is going to be the shader stage of the VK of the pipeline. We're going to put our module in there, and then we're going to have this starting point at main. We're going to do a similar thing for the fragment shader. We're going to say the structs fragment shader info. We're going to say this is going to be the fragment shader part of the pipeline. Load our fragment shader module, say the starting point is going to be main. So after that, we have our VK pipeline vertex input state create info struct. That's it's a big word, a lot of words at once. So here, we're going to rely entirely on the GL vertex index to generate the coordinates. We're not going to be using something like a VK buffer. That's basically what that's saying here. And then for our input assembly, the input assembly is basically how to you're telling the GPU what you're going to do with the vertices and how you're going to connect the vertices. And in this case, we're going to set the topology to a triangle list. So basically what that means is every three vertices form a completely independent triangle. All right, so next we have our viewport. We're telling it to start at 0, 0, the top left corner of the screen. We're saying we want it to be the width and the height of the swap chain. We have our depth range. This tells Vulkan to map the closest possible objects to 0 and the farthest to 1 in the depth buffer. We're not going to get into depth buffer right now, but just putting that out there. And then we have our scissor. This is almost like cropping. You're kind of telling Vulkan where you want to start masking pixels. So what area do you want to, where do you want to see pixels? And in our case, we're saying we want to see pixels across the entire extent of the screen. We have our VP state. We're just saying we want one viewport, one scissor. Inside our rasterizer struct, we have the depth clamp enabled. We have it set to false. If it were true, fragments that are outside the near or far planes would be clamped to the plane instead of being thrown away. That's what I'm reading here. We have rasterizer discard enabled. If you set this to VK true, the geometry never reaches the screen, but we have it set to false. It's like turning off the paint part of the pipeline. That's apparently what it's saying. We have polygon mode set to VK polygon mode fill. That's saying we're gonna fill in the triangle. We're gonna have a line width of 1. Then we have our cull mode. We don't want any culling. And then we have, for our front face, we have front face clockwise. This defines what the front face looks like. So this image from learnopengl.com does a pretty good visual representation of this. Depending on the winding order, which is the order of the vertices on the triangle will determine whether it's front or back facing. The winding order is calculated at the rasterization stage. In our case, we set it to the front face to be clockwise. Then we have VK sample count 1 bit. And remember how I said there's a difference between samples and pixels? They're related, but there's samples within a pixel. So VK sample count 1 bit tells the GPU to calculate the color for exactly 1 point in the center of the pixel. And if you look at this visual representation, it does a pretty good job at describing what's happening, and it makes like a jagged staircase kind of look. Our color blend attachment struct, we're going to have no masking, no alpha blending. So we set blend enable to false. We have this VK push constant range. It's the fastest way to send a small amount of data from your C code to your shader. We create our VK pipeline layout, create info struct. We supply it with that push range. We create our pipeline layout. Then this rendering info is actually part of dynamic rendering. We tell the pipeline how many color images we want to attach during drawing commands. We're just drawing a simple triangle, so we're just going to output, 1 image. We create our VK graphics pipeline info struct. We give it all of the information that we kind of filled out earlier. We're not using render paths. That is because we're using dynamic rendering. We create our graphics pipeline, destroy the shader modules. I then create a destroy graphics pipeline function, and I make sure to call it after the while loop. I also make sure to create the graphics pipeline above the while loop. Also, I didn't enable dynamic rendering, so I made a dynamic rendering struct, set dynamic rendering to true, and added that to the DCI struct in PNX. And that's all for the video. Next, I'll actually record the command buffers, and then we'll actually draw the triangle to the screen.